All right, so in the last video, we took a look at this program. Let me come back to it for just a moment, or looking at the assembly version of it, where we were in two different threads incrementing the same global variable. And we saw that depending on the order in which those threads run, we could have problems. So we had the head, a load, update, store, and then the tail. And if the load, update, and store of two different threads are interleaved with one another, then we could end up with, even though we executed this line twice, count only being actually incremented once. So let's take a look at a way to model that so that then we can see what we can do to solve it. So this is a process graph. It shows what these two different threads are doing. So because these threads are running concurrently, the things in thread 1 and thread 2 can, relative to each other, happen in different orders. But within a single thread, things are happening sequentially. That is, head 1 always executes before load 1, before update 1, before store 1, before thread 1, before tail 1. So what we'll do is plot those out in 2 dimensions. So the x-axis here shows what thread 1 is doing at the moment, and the y-axis shows what thread 2 is doing at the moment. So the fact that things execute sequentially within a thread means we're only ever moving to the right and up, and we're not skipping to the right. We're moving either one step to the right or one step up. But there are many different ways we could go one step to the right, one step up, and so on to get up here. We could follow this path, or we could follow this path, and so on. So a point in this graph is an execution state. So that is what thread 1 is doing right now and what thread 2 is doing right now, depending on its x-axis and its y-axis value. So this point shows a state where thread 1 has just finished the L1, so the load, and thread 2 has just finished S2, its store. So a trajectory is a sequence of legal state transitions that describes one possible way these threads could be executed concurrently. It's a path made up of steps to the right and steps up, going from the lower left corner to the upper right corner. So in this example, thread 1, its head executes, its load executes, its update executes. Then thread 2's head and load execute. Thread 1's store executes and its tail executes. And then thread 2's update, store, and tail execute. So the problem that we had is that there is a critical section. A critical section is a region of code that is referring to a shared variable in such a way that if we do other things in the middle of it, in the other thread, we have problems. So L, U, and S are our critical sections because those are the load of that global variable, an increment of the register it was loaded into, and a store of that register back into the global variable. If something happens to the global variable in another thread while this stuff is running, we have a problem. So we'll mark this as an unsafe region here. So this is this is the place where thread 1 and thread 2 are both doing the critical section at the same time. So they're both doing the load, or one's doing a load and one's doing a store, and so on. So if we have something that goes through this unsafe region, then we're going to end up with potentially 1 as the value of our twice incremented counter. If we avoid the unsafe region, then we're fine. So for example, in this red trajectory, which is unsafe, thread 1 loads the variable, it updates the variable, and Before it gets a chance to store it back, thread 2 loads the variable. Now we're inside this unsafe region. Thread 1 loaded the variable as 0. Thread 2 also just loaded it as 0 because thread 1 hasn't stored it again. And now thread 1 gets a chance to store it, stores the value 1. Thread 2 increments that 0 to get 1 and stores it, also storing 1. And we end up with the value 1 when we get to the end. On the other hand, along this green safe trajectory, which avoids the unsafe region, thread 2 loads, updates the variable. Thread 1, so thread 2 has the value 1 right now. Thread 1 does the head. We don't go to the right here. That would be unsafe. So thread 2 again stores a variable. It has stored the value 1 now. Now thread 1 loads the value 1. Thread 2 finishes maybe, and then thread 1 increments its value 1 to 2, stores that in the global variable count, and finishes. So our global variable is 2. We got the result we expected. So if we can figure out a way to make sure that we don't get into this unsafe region, then we'll be okay. The program will do what we want. So how do we do that? That's called synchronization. We want to make sure that this critical section, so L1, U1, S1, and the critical section L2, U2, S2, are not executing at the same time. So we want to guarantee mutually exclusive access to them. There are lots of different ways to do this. We're just going to look at one of them, and that's called a semaphore. So semaphores were invented by Edsger Dijkstra, a famous computer scientist from the Netherlands. And I mentioned the Netherlands thing because the Dutch language will come up in just a moment. That's not the only approach. There are also things like monitors, which Java uses, condition variables, which pthreads use. So there are lots of different ways of enforcing mutual exclusion. Most of these other things can be, not necessarily are, but can be implemented on top of semaphores. So what's a semaphore? Well, it is a variable, a global variable shared among the threads that is used for synchronization. We are also going to guarantee it's non-negative. That doesn't mean we'll make it unsigned. That means in the way we use it, we will ensure that it never becomes negative. And we have two operations to modify it. So what is a semaphore outside of computer science? Well, this is a flag that's used for messaging. Ships will often use semaphores, or at least more often before radios existed, but still do, use semaphores, use these flags with different colored patterns to send messages to other ships from a distance or to a port from a distance. And likewise, the port could use semaphores to send a message back to the ship, telling them which pier to dock at, for example. So we have two operations on semaphores called P and V. And this is where the fact that Edsger Dijkstra is Dutch, or was Dutch, comes in. P stands for proberen in Dutch, which means to test. V stands for verhogen, which means to increment. So you can think of them as test and increment, if that makes it easier to remember. But P and V are what they're usually called in the computer science literature. So the P operation, if our semaphore is non-zero, then it decrements the semaphore and returns immediately. Those have to happen atomically, indivisibly. We have to do that in such a way that no thread can come in and do something with S while, or in between that, checking if it's non-zero and decrementing. If it was able to, we would have exactly the same problem we just saw in our bad count example. Fortunately, the CPU provides ways to do that, to have an atomic and indivisible load and, or decrement and test operation. If So that's if the semaphore was non-zero. If it is zero, then, well, we are guaranteeing that it will never be negative, so we have to wait. So if it's zero, we'll suspend this thread until it becomes non-zero. And then when it becomes non-zero again, we will go on and restart this operation, decrementing and so on. Well, how would it become non-zero again if P only decrements? Well, that's what V is about. The V operation increments the semaphore. And also, so that increment does have to happen atomically. We can't do a load, update, and store as 3 separate instructions. We have to make sure that that happens all at once. Fortunately, x86-64, its increment instruction is atomic. But then there is another problem, which is, or another thing it needs to do, which is if someone was waiting, we just incremented the semaphore. It might have been zero. Once we increment it, it will be non-zero because it can never be negative. So once we increment it, if any threads were running the P operation and suspended because of that, then one of those will be restarted. And that allows that other thread to then go and do its thing. So as I mentioned, there's an invariant here that S is never negative. Because the only way it could become negative is if it were zero and we decremented it. But if it's zero and we tried to decrement it, we will instead suspend the thread until it's non-zero and then decrement. So there are pthreads functions for working with semaphores. There are 3 important ones. Seminit initializes a semaphore. Now a semaphore has this integer variable. It needs an initial value. Usually that initial value is 1, but it could be greater than 1. The initial value is how many times we're allowed to call P before we start suspending. SemWait is the name for P, so that takes a semaphore. If it's positive, decrements it and doesn't wait. But if it's zero, waits for it to become positive again and then decrements it. And semPost is V. It increments the semaphore, and if someone was waiting for it, it wakes them up. There are a couple of wrapper functions provided in CSAPP for that, called P and V, which check the error value and so on. So that also makes it a little closer to the usual computer science terminology instead of the POSIX terminology. All right, let's take a look. Well, we looked at bad count, which unfortunately is being cut off here, but it's the same thing we saw in the last video. So let's see how we can use semaphore for mutual exclusion. The idea is we'll make a semaphore. We'll call it here mutex, which stands for mutual exclusion. We'll make it 1. That means we can only call P once before someone calls, or well, we can call it more than once, but it will only be decremented once. P will only return once until someone calls V. So there are different kinds of semaphores. A mutex is a binary semaphore, meaning its value is always either 0 or 1. It's possible to have a semaphore whose initial value is greater than 1, which would allow, say, 2 things to run this critical section or to run this section of code at the same time, but not 3. It's not so often that we need that, but there are some situations where that arises. But a mutex is specifically a binary semaphore that we're using to provide mutual exclusion, to make sure that we're only running one copy of that critical section of code at a time. The P operation locks the is also called locking the mutex. That is, we are taking that mutex for ourselves. No one else is allowed to use it. If someone else tries to use it by calling P, they will be suspended. They will wait until we're finished with it. And the V operation is unlocking the mutex, also called releasing it. and we say that we're holding the mutex in between the time when we lock it and we unlock it. So here is a program that it's a version of bad count, but it's called good count because it does that. It does that mutual exclusion. So we have this global variable mutex. Semaphores have this type sem_t. That's probably, depending on the operating system and CPU architecture and compiler and so on, it's probably just an alias for an integer, but that can depend. So we'll use the official type name. We'll start out by initializing the mutex with the value 1. We'll start our 2 threads, and then within the threads, each time we go into this loop, while we're doing this part, remember this was our critical section. It does a load, an update, and then a store. And if someone else interrupts us, or if someone else does a load, update, store on the same variable at the same time, that would be bad. So before we start that critical section, we'll lock the mutex. And then after we're finished incrementing, we'll unlock or release the mutex. So if the 2 threads were trying to run this at the same time, one thread would get a chance to do this P, which is atomic, meaning it can't be interrupted. Other threads can't do anything with it while that's happening. Then it would increment, then it would release. But if while it were in the middle of incrementing, the other thread tried to do that, this P operation would pause that thread because the semaphore's value is already 0. The mutex is already locked. So only when that first thread unlocks the mutex does the second thread finish this call to P and increment the count. And if we run this program, no matter how many times I run it, it's always going to tell me okay. There aren't any situations here where I could end up incrementing the variable the wrong number of times. So the idea there is we're making a forbidden region in the execution graph. So I'm also labeling here each node in the execution graph with the value of the semaphore. So we've added a few more steps because besides the load, update, store, there's also this P operation. So after the P operation, the value of the mutex is 0, and the mutex, the way the P and V functions work, guarantees it will never be negative. So this region where the value of the mutex would be negative is forbidden. And that region encloses the unsafe region. It's not exactly the same as the unsafe region because the unsafe region doesn't actually include this particular node, but the forbidden region does. All right, so the idea then is that programmers need to have a good model of how variables are shared by threads. If we are sharing variables, they need to be protected to ensure that they are accessed mutually exclusively, and semaphores are one way to do this, and in some sense the most fundamental way. All right, that's all for this video. We'll see a little bit more about threads and thread safety in the next. Thanks.